You have questions on anything before we get started?
No, I haven't started. You want to switch to tablet mode?
No, I don't want to switch to tablet mode.
How was it test?
For
I haven't written it yet.
6.52, it says find a one-sided 90% confidence interval. Do we do that the same way that we would find a regular confidence interval, but only find the one side?
So yeah, you don't. If you're doing one-sided, you don't split the alpha in two. You do a z sub alpha instead of a z sub alpha over 2. And then if it's for proportions, it depends on which way the one side goes. So if you're looking for, if you find an upper bound, then your lower bound is going to be 0. Then you find a lower bound, your upper bound will be 1. Because your proportion can never be less than 0 or greater than 1. So that's how you do your left or right endpoint for that. But otherwise, you do it the same way.
Okay.
Cool. Other questions at all? You stepped in a puddle?
Yeah, I had to walk back from softball practice while it was raining. I stepped in a puddle. It was really cold.
Yeah, it would be cool. Yeah.
Actually, can you explain one more time how to find the z?
For
any problems?
probably the easiest way to do it is just to do it on Excel.
What was the question?
How to find the z sub alpha or alpha over 2.
Oh, okay.
So, for instance, we're going to do problem 6.6-7. So, we talked. This is stuff we did talk about with sample size last time. So, in 6.6-7, they want to know how large of a sample do you want. If we want the maximum error to be 0.03 with 95% confidence. So remember, for your proportions, your endpoints of your confidence interval look like this. Right? And then, depending on what you're doing, either you're going to plug in p hat for p, or use the biggest possible value you can, or use the value, you make the numerator as big as you possibly can. I guess I should say it that way. So in this problem, they don't give you a p hat even. They don't give you anything. They just said, how large of a sample do you need to start before you do anything else? If you're trying to estimate the population parameter, the population proportion parameter, I should say, to within 0.03 with 95% confidence, then I'm going to need to make this as big as I possibly can. What's the biggest that I can ever make this thing? 0.25, right? So you use 0.5 for p and make that 0.25 in there, right? So that maximizes, I should read my handwriting, that maximizes the numerator, right? So the equation that we'll solve is the z sub alpha over 2, which in this case is 0.025, times the square root, I'll write it this way, 0.25 over square root of n equals 0.03. Oops, this should be 0.5, shouldn't it? Thanks. Square root of 0.25 is 0.5. Right, square root of a quarter is a half.
Yes.
I agree.
Okay. All right.
Math checks out.
So the math checks out. Good. All right. So this value here is what Megan was asking for a reminder of how to find. Yes. Okay. So if I do that in Excel and grab a keyboard. So if we use the it doesn't matter which one you use. You probably want to use the standard one, the norm.s.inv. That way you want to try, if you use the norm.inv, you have to type in a mean and a standard deviation. Okay? The norm.s.inv, the .s means the standard norm. So you want to type in, it assumes mean 0 and standard deviation of 1. So if we use that one, the probability that we want, we're looking for the right tail in this case, because we're looking for that z sub alpha over 2, the one that gives us a 0.025 on the right. So put in 0.975. If you forget and put in 0.025, it'll just give you the negative of what you want, since it's symmetric. So it doesn't really matter which one you type in. Yeah, Morgan.
So how do we know we just want the right tail of this? Like,
Oh, you always want the right tail for that one. It's always the positive z that we want. That's why we use plus or minus, because it doesn't matter which one we use. I mean, if you use the positive one, the minus will give you the negative one. And so we get the 1.96 like we typically do here. So if we go back over here, you would use 1.96 and 0.5 over square root of n equals 0.03, and then solve for n. What do you get when you solve for n here?
Hey, Michael, nobody asked. I got a really big number, like 1,067.
Okay.
You round up or down, I forgot.
Always up.
8, sorry.
Oh, wow. You should have made the other line a little bit bigger so that it looked more like an 8. It still looks like a 7. There you go.
Is it better? All right. One thing to notice is that if you're looking for quick and dirty, what does that approximately equal there that I just circled? 1, right? So 1.96 is about 2, isn't it? Okay. So you can make this 1, and this that your n needs to be approximately whatever your 1 over your margin of error is squared. I should say desired margin of error. Yeah, well, it should be different because you didn't use 1.96, you used 2. You got something a little bit bigger? Yeah. And should have. But you can use that just as a rough guess, a rough estimate for what you need. Which is probably all you're looking for anyway if you're trying to do polling. Because you're going to just go survey people, a whole bunch of people until you get enough.
Yes, survey 1,060 now. People come up. Exactly.
Exactly, 1,068 people, right.
So accurate.
Yeah. And so the only thing that's going to change is depending on what confidence interval you want, or confidence level you want, will change your z value. What margin of error you want will change that value. The smaller this number gets, the bigger n you're going to need. The more confidence you want, the bigger n you're going to need. Because notice when you move things around, you'll multiply both sides with the square root of n, and the desired margin of error goes in the denominator. So more confidence, higher confidence level obviously increases your z, which will increase the n that you need. Lower margin of error, go in the denominator over here, will increase the number of n you need. Right? So if you want more confidence or a better estimate, you need a more sample, which is a rule of thumb in statistics. If you want something more accurate, you need a bigger sample. It's about the only way to guarantee that you're going to get better estimates. Again, most of why we look at all sorts of different ideas behind sampling and estimating and all of those good things is in a lot of real world scenarios, you're limited as to what the size of your sample can be. For polling, you're not really limited. You're only limited by how you contact people, right? For polling, what you're really worried about is making sure that your sample that you're taking is not biased. Did I just talk to my friends in class to try to get an idea of what's going on campus-wide? Did I go outside of a casino to poll people on whether or not they should be allowed to smoke in public buildings? If you've ever been to a casino, you'll know why I said that.
I guess.
So there's lots and lots of different things that can cause bias in your sample. So that's what you're more worried about with polling, is making sure that your sample is not biased. That's what happened in Iowa not too long ago with the caucus. I mean, besides the mess that they had with the app, whatever they were using wasn't working. They didn't release their last poll because they had issues with how they selected people for their last polling for the caucus. So they didn't release the last poll before the caucuses. They actually were worried about it being biased and having the results not biased. So they didn't release it. So as far as polling goes, that's the biggest worry that you have, is making sure that the sample you're taking is as representative of the population that you're interested in as you can. Yeah, Grace.
Kind of off topic, but not really. Are we gonna finish content that's gonna be on the test today, or?
Probably Wednesday. Don't make a frowny face.
I didn't know if we were gonna have a review day.
We'll review some on Wednesday, because I'm going to start the last new stuff today. Yeah, I just don't know if I'll get all the way through it, but I'm going to start it.
We'll try.
We'll try. Are we okay with finding sample size then? I mean, the concept's not too bad, right? Okay. All right, so let's talk about 6.7, which we've actually talked about a little bit before last semester. And if you're in regression analysis, you've probably already talked about this stuff anyway.
Oh my gosh. Regression.
Sorry.
You know how much I love this class right
How much do you love, what, my class? Oh, regression? I don't know what to tell you.
We love regression.
All right. So we're going to do just simple linear regression for one variable. Good grief. Sorry. The concept, though, extends to multiple regression for having multiple inputs for a single output. Good grief, sorry. Goodness. I don't know what that was. Anyway. So in section 6.8, they go through multiple regression stuff. It's the same idea as this section, just with multivariate inputs rather than a single variable input. So we're not going to go through that part. We're just going to go through this part. And we talked about some of this last semester as well. The idea is that you're given sample points. And you're interested in fitting these with a linear model. By the way, the idea behind the linear model means it's actually linear in the coefficients, not linear in the variable that you're talking about. So if you were trying to find an A, a B, and a C, to fit y equals ax squared plus bx plus c, that's still considered a linear model. It's not the shape of the curve, it's the linear in the variables. Because you're given the x's and the y's. You're interested in it being linear in the coefficients, the a and b, the c. That's a linear model. So just as far as terminology goes, we're not going to do quadratic models for these, or trying to fit it with a quadratic function, but that's still called a linear model because the coefficients are linear. Okay. Anyway, so the idea, of course, is to try to fit the data to this type of point. So what we're interested in trying to do is figure out the differences from a particular point down to the line, whatever this distance happens to be, for all of these points, there is a distance, right? And the idea here is that we want to try to minimize that error as much as we can. Those are all errors. We want to try to minimize that as much as we can based on the form. All right, so we're going to take our individual y's, so we'll write it y sub I. We're going to assume that it is linear in alpha and beta. And I'm going to write it a little strange. This should be epsilon sub I. So we want to use the same alpha, we want to use the same beta. The error will change depending on the I. We're only writing this in this particular fashion to help with computations later. But the x sub I changes, this x bar will be fixed for a particular problem, right? Because we're doing it for a particular sample, I should say. We have to make some assumptions besides the fact, though, that a line fits this value as it shakes. Okay, we have to make some assumptions about the error. So we're going to assume that each of our errors is normally distributed with a mean of 0 and some variance sigma squared. And this is for every single I. So we're assuming that our error is normally distributed. Whether or not that's a valid assumption depends on, well, mainly sampling methods, but we, of course, would want our average error to be 0 if we did this over and over and over and over and over again, right? And we're going to assume that the error has a common variance. Essentially what that means is that when we're doing our errors, we're assuming that the error is coming about by something other than how x and y are related to each other. It's independent of how the x and y are related to each other. Okay? The error is being caused by something else, if you will. Of course, since we have a random sample, we're going to assume that all of our y sub i's are independent because it's random. Okay? So when we pick these things, we're going to assume that they're independent. Clearly, at least I hope it's clear, that if we've got some sort of a linear relationship between x and y, the x and y are not independent of each other. Right? No, it wouldn't make much sense. All right, so the idea here is to try to get estimates for the alpha and the beta based on the sample that we're given. The way we were going to get these estimates is to look at maximum likelihood estimators. Okay. So to start with, let's look at what has to be true about these. All right, so each of these epsilons are normally distributed, right? And we know that the y's are all independent of each other. And this thing, this is the random variable, but this is a constant, right? We've observed the x sub I. We're looking at the distribution of the y sub I. And this is a random variable based on the error, right? The idea behind this is that we've obviously observed the y's, but the y might be different than what they're supposed to be based on the x's. If we don't have error, we know exactly what the y's are because there's a linear relationship between the x and the y. Right? If we have no error, once we pick the x, we know exactly what the y is. Right? If there's no error. So if we pick the x's to start with, what we're really doing is sampling the y's from an error. The x sub I minus x bar is a constant. Okay? The things that vary are the y's depending on the error, however we're doing the selecting. Okay? So, if I move everything over to the left-hand side, what I have is some constant subtracted from the y sub i's equals the epsilon. So each of our y's are also independent of each other, and they're all normally distributed. Right? So if we think about it that way, if we look at the epsilon sub I is, right the other way around, y sub I minus alpha minus beta times x sub I minus x bar. Okay. This is a normal, well, this is normal, so this implies that the y sub I is normal and independent. I should say the y sub i's are normal and mutually independent. This is important because we're trying to get a handle on what alpha, beta, and the sigma squared are. That's the whole idea behind this. I wanted to get a handle on what alpha is, what beta is, and what sigma squared is. To be able to do that, I need to find estimates for those things. We need to use methods that we've already talked about to help us find estimates. One of the methods that we talked about was maximum likelihood generators, or estimators, sorry, maximum likelihood estimator, I don't know why I said generators. The way we get maximum likelihood estimators is to do products of PDFs, take logs, and differentiate, right? Okay. To do that, I need a PDF, right? All right, so we know this distribution by assumption. It's normal, mean 0, standard deviation, or variance sigma squared, right? So its PDF for the epsilon sub I should look like a normal distribution. Well, we also have all of these other particular things in there, but when I have that normal distribution, I can multiply them all together to give us the joint PDF, if you will, of all of the random variables for the epsilon sub i's. So to do this, what do we need to do? We need to multiply all the PDFs together. Well, we have to remember what the PDF is for the normal. For your normal distribution, you have 1 over square root of 2 pi sigma squared, and then it's e to the negative x minus mu quantity squared over 2 sigma squared. Okay? What's mu in this case, though? 0, right? And this is our variable. The epsilon is our variable in this case, so the right-hand side is our variable. So we'll have e to the negative y sub I minus alpha minus beta times x sub I minus x bar, that whole thing squared, over 2 sigma squared. And we'll need to multiply all of these things together. This is our likelihood function, right? And the reason why we have a likelihood function in 3 parameters is because there's 3 parameters in there. I don't know alpha, I don't know beta, and I don't know sigma squared. I know, there's so many of them. But this looks like maximum likelihood generator stuff that we did, right? Take your PDF, call it a PDF on a sample, multiply it all together, right? If I just called this variable epsilon sub I, this would be exactly what we did for maximum likelihood generator stuff before, correct? The reason why there's not a minus mu here, of course, is because we already said assuming the mean 0. Right. Now, what did we do? What was our first step when we did these to help us find the maximum likelihood to estimators? What did we do first? Took the natural log, right? Okay. Now, what we're interested in is maximizing this now with respect to the parameters But of course, remember, if it doesn't involve a parameter that we don't want to maximize with respect to right away, we could ignore it essentially. We're interested first in the alpha and the beta. We'll worry about the sigma squared later. We're interested first in the alpha and the beta. If I assume that the sigma squared is constant, which it is, if I take the log, it'll change this into a sum, right? Okay? And it'll break this into a sum as well. Does this have any alphas and betas in it? No. So if we differentiate with respect to alpha or beta, this will go away. Right? The same thing happens here. When we hit the log here, I get this expression that's left, the sum of that thing, right? Okay? I've got this in the denominator, but again, that's just a constant. If I can maximize the numerator, it'll maximize the fraction. Right? If the 2 sigma squared doesn't have an alpha and beta in it, all I really need to do is maximize the numerator, correct? Okay. And if I notice I have a negative in my numerator, to maximize the negative, I can minimize the positive, right? So this whole thing boils down to this problem simplifies to minimizing, I'm going to call it little l of alpha beta, the sum I equals 1 to n of these things.
The L is a random letter.
I just used L, little l because it was the capital L, yeah. The book used an H, which was really random. Okay. It has something to do with the original problem. That's why I used the same letter. Did everybody see why that simplifies to minimize? Yeah, Morgan.
So like why do we now we want to now minimize the alpha beta? Or like
We're trying to do the maximum likelihood estimates. If I want to the maximum of this thing in terms of alpha and beta depends on the numerator. But the numerator is negative. So to maximize the negative, I would minimize the positive.
okay.
Because it flips, negatives flip, if I multiply both sides by a negative, it would flip the inequality if you think about it that way.
Okay. So then why do we know to look at alpha and beta right now?
Those are the unknown pieces. I mean, we don't know the epsilon either, but these are the unknown pieces here that we're trying to figure out for the linear model. So we're trying to get an alpha and a beta that best estimates our model for x and y. That's the idea. Okay. That's why we're ignoring sigma squared too right now, because what we're interested in finding is the alpha and the beta. We also want to do it. I mean, we need to know something about the error if we can to help us know how good the model is. But right now, we're just trying to figure out what the alpha and the beta is that gives us our best chance of finding the best model that we can. That's the idea. All right. Are we okay with why we're minimizing? After taking the negative off, rather than maximizing with the negative on? Okay. All right. If you've had this before, if you've looked at this before, notice that we're trying to minimize something with a sum of squares, or it's called the least squares. That's why it's called this, right? We're trying to minimize this thing with a square. What are we trying to minimize? Here's a predicted value. Here's an observed value. We want that to be as close to 0 as we can get it. Yeah. This is a predicted value because I've put it into the linear model. I know it looks a little bit odd the way I have it written, but we're going to do that for just basically for simplification case sake. For ease of computation, I should say. These are the observations that were associated with the x of I. So the difference between them is giving you assigned distance. Now again, if we add up all just deviations together, we should be getting 0. That's why another reason why we need to square it, because I want to make sure we get a measurement somehow of the deviations. Now again, another way to do it instead of squaring is do absolute value, which is harder to minimize. All right, but anyway, this idea of least squares is coming out of the maximum likelihood estimator again. All right, so if I want to maximize this thing, I need to do partials, which is not too bad. I think we did this last semester, actually. If I do the partial with respect to alpha, notice there's a negative in front of the alpha and no other coefficient, but I still have to use the chain rule, right? So I'll have a -2, because the derivative of the inside there is a negative, and then a sum of I equals 1 to n, y sub I minus alpha minus beta times x sub I minus x bar. No squared.
Why is it?
2 came down in front, derivative of alpha is a -1. It's those two things together. Yeah? Do the same thing for beta. Instead of a -2, we're going to get a -2 times this expression here, correct? Okay. Okay, we're maximizing a function of two variables. We need to solve them both equal to 0 simultaneously, right? Good news is that isn't that bad. Look at this the third term here. If I break up this sum over these three terms and just sum up that last term, what do you get? 0. Why? Good. Yeah, when you sum up your deviations from the mean, it's always 0, right? Think about it this way. This is a constant. So it's used to get n times x bar. But x bar is 1 over n times the sum of the x's. So that just becomes sum of the x's, and this will be sum of the x's. So you'll get 0. That deviation is always 0, right? Some of the deviations is always 0. Okay? So if this is 0 when we set this equal to 0, the only thing I'm left with is this part. And then the -2, I can divide it out and set those pieces equal to 0. So if we do the partial with respect to alpha equals 0, that's going to give us that alpha, if you go through it, will be the mean of the y's. I know I skipped a bunch of steps. Okay? Do we all understand why this term is going to go away? When you sum the deviations, you get 0. You get the sum of the x of i's minus the sum of the x of i's when you're done. Yeah, that makes that 0. If I've set this equal to 0, I can divide both sides by -2. Right? So it's still 0. Sum of alphas is going to give you n times alpha. Right? So when I solve for alpha, I'm going to have the sum of the y's over n, which is the mean of the y's. Right? Right?
So that ends are canceling out.
Because this will be n alpha, so I'm just moving, they get 1 over n, sum of the y's, which is y bar. All right, so that means that our maximum likelihood estimator alpha hat will be that same y bar, the random variable y bar. That one pops up nicely. It's easy to see now that alpha hat is an unbiased estimator for y bar, or for y, I mean, right? Because the expected value of y bar is the same as the expected value of y, right? So it does give you a nice unbiased estimate for alpha, which is what you want. Now if you do the one for beta, I'm not going to go through all the algebra at all. You could read it in the book if you really want to. It's not that bad, it just looks worse than it is. The thing to notice in this case, where these pieces are coming from, if you distribute your x sub I minus x bar, which of the terms is going to add up to 0? If I distribute this over this, which of the terms is going to add up to 0? The alpha term will add to 0, right? This is not a constant, but this is, correct? So when this term getting distributed will make the alpha term go away. So you just have these two you need to solve for. And that's where those pieces are coming from here. Yeah, Morgan.
So why wouldn't your one side, your x sub I minus x bar, why would that go away?
So this one's not going to go away because of the distribution of this piece here. Actually, you know what? I've written this in the wrong spot. This one can't be on the outside. Sorry. This needs to be on the inside. I got a little excited when I factored it out. Sorry. I can't factor that out because there's an I. Right? I can't pull the x sub I out of the sum. The 2 I can still pull out, but I can't with the x sub I. Now you can see why this one's not going to add up to 0, because if I distribute that through, I get an x sub I minus x bar squared. Instead of, the reason why I cancel out the other ones is because you have some positives and some negatives that are canceling each other out. When we get the squared, it won't cancel each other out. Each individual one would have to be 0 for that to happen. How did I get here? So we distributed this through, right? Okay. That term goes away. So I've got 2 pieces, and remember it's set equal to 0. So I would have the beta is multiplied by this thing. I have to divide it over to solve for beta. That's where it's getting in the denominator. Okay. All right, so this is where your beta hat comes from. You can do a similar thing with to figure out your sigma squared. Oops, that's not where the squared goes. And it looks like the following, which is not a huge surprise. Oops, I put the square in the wrong spot. It's not a huge surprise, that's where that comes in there that way. Good news is I'm not going to make you memorize these formulas.
So are these all to like help find the distances between the point and the regression line?
Yeah.
So you could use
That's what all of these are here.
And then what are the partials?
The partials are making sure that we're finding the maximum likelihood estimator. That the alpha and the beta give us the best fit that we can.
So we wouldn't need to use those when we're looking for the distance.
No, we do need to use those because that's what's helping us get the distance. Those alpha and the beta help us get the graph of the line to figure out our best guesses for what the errors are.
Because then you would put in your y sub I what you observed to find it.
Yep, that's right. We're trying to make our best guess at what the parameters are. The parameters in this case are the alpha and the beta. So we're using the derivatives here to get us these formulas to help us figure out estimates for the alpha and the beta. All right, so what we're interested in with these are their distributions. So if we look at just this piece here without the n, we'll worry about that in a minute. If I just look at this part, I know I'm skipping a lot of algebra, but basically it's because I don't expect you to reproduce all the algebra ever. All right. You can rewrite this as, make sure I get it all the pieces down here that I want. All right. This simplifies to the following. I mean, we could go through the algebra if you really, really want to, but I don't figure you really do. The whole point of this is I want to get to the distribution of this. This is on the top of page 327, by the way, if you care. Gosh. If I could write an alpha instead of an A, I'd be happy too. Okay. All right. What's that? What's for? I'm going to tell you in a minute. All right. So, some of the stuff that we need. What kind of a distribution did each of these have in here? Normal, right? Now, I haven't divided by its variance. But if I did, I would divide by sigma squared, right? If I divide this by sigma squared, what kind of distribution does just that one piece on the inside have? If I divide this by sigma squared, what kind of distribution does this have? It's standard normal on the inside of a square. When we square a standard normal, what kind of distribution do you get? Chi-squared on how many degrees of freedom? 1. How many of them we're adding up together? N, right? Right? So I have to divide it by sigma squared, right? If I divide this by sigma squared, this side, it becomes chi-squared of n. And again, this is after dividing by sigma squared. Okay? All right. How is alpha hat defined? Y bar, right? What's the expected value of y bar? Well, it's just the same as the expected value of y, isn't it? This is going to turn out to be this alpha. The reason why it's going to be alpha is because remember the y is the alpha plus beta plus an error, right? The expected value of the error term is 0. The expected value of this term, the way we have it written, is 0, correct? All right? Okay. Remember your y. Your y, I'm not going to write this sub I. You know, maybe I will. That's our y sub I, right? Okay. What's the mean of this piece? 0. If I add these up, what do I get? 0, right? So the expected value of alpha, which is y bar, is the same as the expected value of y. Right? It's going to have the same expected value. These expected values here will be 0. Okay? And what also happens to the variance, though, when you do the variance of y bar? It becomes sigma squared over n, right? Okay, so let's look at this piece right here. If I divide that piece by sigma squared, what does it look like? So we get alpha hat minus alpha. Alpha hat's going to be normally distributed because y is, right? Alpha hat was y sub I. Or the mean of the y's, sorry. This is normally distributed. We're subtracting off its mean. Its expected value is alpha. And then we divide by sigma squared over n, essentially. We'll have standard normal again, squared. Right? If we divide this by sigma squared, all right, so let me write this down. The expected value of alpha hat is alpha. The variance of alpha hat is sigma squared over n. This is all due to the fact that your alpha hat is y bar, right? Yes? Expected value of y bar is the same as expected value of y. Expected value of y is alpha. Right? If I do the expected values here, I get 0 and 0. Yeah, Chris.
I don't know that the expected, or that the variance of alpha hat is the variance of n.
What's the variance of y bar? How do you do variance? What's central limit theorem tell you? What's the variance of y bar?
I'm just gonna guess variance squared of n.
Variance over n. Remember, that's what you do with the variance, right? When you do for, because you've got, if you want variance of a mean, it's that, right? That's how you define y bar, is it not? Because
I might just be pointing today. I believe
how do you find the mean?
the mean.
Yeah.
Day by day, I just go.
If I have well, you want to find the mean, how do you find the mean? You sum it up and divide by n?
Yeah.
Yeah. What do you do with this constant when you pull it out in front? You square it. When they're independent, what happens to the variances? They don't go away. You add them up when they're independent, right? Remember that from central limit theorem stuff? No?
Yes.
Yeah, but that's where this is coming from, right? All right, back to what I was doing, because I want to finish this up in 2 minutes, and I've got a lot of scribbles on the board, on the screen. All right, expected value. What kind of variable is alpha? Well, it's the mean of alpha hat. It's the mean of a normal distribution. Mean of normal is normal, right? It's normal. What's its mean? Alpha. We sort of dragged it off its mean, right? If I divide this by sigma squared and pull the n down to the denominator, I've now divided by its variance. What kind? So I've got normal, standard normal, essentially squared. So what kind of distribution does this have? It's chi-squared on 1 degree of freedom. The same thing's going to happen here on this one. We didn't do the variance of this one, but trust me that that one's also going to be chi-squared on 1 degree of freedom. Okay. All right, so let's look at the pieces, and then I'm going to stop. Look at the pieces. This piece is chi-squared of n, made up of a chi-squared on 1 degree of freedom plus a chi-squared on 1 degree of freedom plus this piece. Just based on the way the pieces are going and fitting in together, what kind of distribution do you think this is going to have? Chi-squared on how many degrees of freedom? N minus 2. And that's exactly what happens. Why is it n minus 2? How many does this one have? How many does this one have? How many does the total have? N. So it has to fill in the rest.
I thought we were talking about total.
No. That specific one has chi-squared of n minus 2. This is your sigma squared hat piece, essentially. Remember? Here's your sigma squared hat. So this gives you an idea of how the sigma squared is distributed. That was the whole reason why I wanted to go through it, was to talk about the distribution of just that piece. But notice that you lose 2 degrees of freedom on this. Think about it this way. In general, if I had a random sample with n pieces to it, I would have n degrees of freedom. If you think I'm selecting n things randomly, I've got n degrees of freedom, right? But how many things do we have to estimate to get to this? Well, to get to the sigma squared, how many things do you have to estimate? 2, right? So you end up losing 2 of your degrees of freedom because you have to make 2 estimates to get to that third piece. I lose a degree of freedom by estimating alpha. I lose a degree of freedom by estimating beta. And this happens generally as we go through more and more stuff this semester. When you make an estimate, you lose a degree of freedom. And notice the same thing happened with sample variance, right? You're estimating population variance by sample variance. What happened when we do the chi-squared? We lost a degree of freedom. Because we're trying to estimate the population parameter from a sample. And this happens generally. All right. Call it a day. We'll do more of this on Monday.